So today we are at 6.2, the mole and chemical formulae. Previously, what we did is that we understood what relative atomic mass was or how to calculate molecular masses or formula masses. And then we saw at different kinds of formulae and we understood what the brackets in the formulas meant or what the dots usually with the water crystallization in the formula meant, and then we went ahead, we did the percentage composition part, different types of percentage compositions, and how we can calculate it. Then we practiced it. And finally, we are here. During this course of study, we also discussed a couple of laws, law of definite proportion, law of conservation of mass, and that exact law of conservation of mass is also shown over here, which gives you the idea that the number of grams of the reactants and the total sum of grams or mass of products is the same, so that we conserve it. When I come to the word mole, mole is a chemical counting unit. So what I tend to explain is that what is mole and how the mole is useful for quantitative chemistry. Now, in order to explain it, I'm going to go to the whiteboard and we are going to cater some examples. Remember, this is the standard unit for the amount of substance in chemistry. The word is mole itself. When we talk about the unit, we simply don't write the part E. I mean, this is the quantity itself. And when we write units, we don't write the letter E. So MOLE for mole, and for the units, it is called mole, but we write it as MOL, the short form. So you are going to see some examples over here. He's also going to discuss about Avogadro's constant or Avogadro's number. He's going to talk about the moles formula. So I am going to talk about all of that, but with an example first. So let's move on to the whiteboard and let's discuss a few examples. Now, we needed the unit mole because mole was very important in terms of amount of substance in the lab. Why? Now that's a big question. That's $1 million question. Uh, in the lab, we actually deal with all states of matter. I hope you are familiar with state symbols. And when we write a chemical equation, we commonly use the state symbols next to the symbols or formulas within parentheses. I hope you already know that S stands for solid, L stands for liquid, G stands for gases, and AQ stands for aqueous solution. Now, we are supposed to deal with all of these phases or states of matter in chemistry lab. And of course, we are going to purchase chemicals and the stuff from the market. So when you go to the market, the things are not all based or purchased on the same quantities or amounts. For example, if I talk about solids, what you most commonly do is that you consider their mass for purchase. There are a lot of things when you go to the market, you purchase them in the units of grams, maybe kilograms, maybe pounds, right? You purchase your simple grains and every eatable material that you purchase, childish material, like I'm talking about biscuits and bubble gums and toffees and all of that kind of stuff, and usually in grams. If the stuff is heavier, of course, kilograms. When we talk about cakes, cakes around the world are usually sold in pounds, not in grams or kilograms. I hope you're familiar with these units, right?
Yes, sir.
Okay, so if I don't take that example and I move on to liquids or gases, I hope you understand that you purchase them on the units of volume. So what we commonly do is that we purchase them in decimeter cubes or liters. If we're talking about smaller volumes, we may purchase them in centimeter cubes or milliliters, right? For example, if you go out to buy Coke, Pepsi, Sprite, name a fizzy drink. These are the most popular fizzy drinks around the planet. You purchase them in what? 250 cubic centimeter, one of the most common 500 cubic centimeter, which is also considered as zero point 0.5 liters, right? Then there is 1 liter bottle, usually. Then there is the 2 liters, sometimes 2.5. There are different sizes in different countries. I hope you're familiar with them too, right?
Yes, sir.
Now, there are a few things which are not based on mass or volume either. When you try to go and purchase them in the market, they're based upon simply the quantity, and the quantity is usually based upon simple counting numbers. For example, if I talk about eggs, you're going to buy them in dozens. When I use the word dozen, I hope you understand I'm talking about 12, right? Half a dozen, 1 dozen, 2 dozen, so on and so forth. Fair enough?
Yes, sir.
We usually do the same with bananas, something that is loved by minions around the world. Okay, so they are also considered in dozens, right? But it doesn't exactly stop over here. We've considered solids, we've considered liquids and gases, but we are yet to consider aqueous solutions. So when you're going to go outside to buy solutions, you are going to see units of concentration, right? For example, this actually applies to your juices. This actually applies to, let's say, we can commonly say medicine. When I talk about medicines, I'm actually trying to be specific about syrups. Like, let's take cough syrups as an example. When you go out to buy cough syrups, they are present in the units of concentration. They tell you that they have mixed the medicine along with water. They have packed it in a small bottle, and hence syrups. Juices are no different. We have juices usually packed in many different sizes. Sometimes they are available as simple volume, but most of the time you will see the concentration, even if it's a fruit juice, the concentration of how much exactly the fruit juice is in there would be written, and the amount of dilution with water is also written. I hope you have seen it, right?
Yes, sir.
If you haven't, I would suggest next time you buy your favorite juice, go ahead and move around the flap, and you would definitely see on the juice box or on the juice packet that on some of the sides it must be written what percentage of that is juice. It's a 30% juice, or it's a 50% juice, or it's a 20% juice. Let me tell you, it's never 100% juice. They always mix some preservatives, additives, some water in there to balance it a little bit. All right. So it might be something like that. So when you're going to
Yes.
go to the market, purchase stuff in many different quantities, and you're going to bring them back to your lab, how are you going to interconvert them? This is really difficult to deal with. If one of the things is your reactant and the product produced is in a different phase, how would you convert it? You don't have a standard for them. The standard for mass is grams, which is separate for the standard of volume, which is decimeter cube, which is separate for counting. Counting has nothing to do with volume or masses, and the concentration is entirely different, which is usually taken in the units of mole per decimeter cube, right? So all of that is different. So we actually needed a middle standard unit to which we could be able to convert everything. So what we do is that we convert this volume into the standard. We can convert this counting into the standard. We can convert this mass into the standard. And we can convert this concentration into the standard. Because of which, you are going to face 4 different formulas for mole in this chapter. One formula is going to convert mass to mole for you. The other formula is going to convert volume to mole for you. And then there would be counting to mole for you, count or quantity to mole for you. That would be another formula. And finally, concentration in mole for you. So that's what this chapter is going to be about. And students are confused. There are so many formulas, we don't get it. If you're going to make sense out of it, only then it's going to become easy. Otherwise, if you keep running away from it, you don't understand what this is about, this is never going to make sense. It would always be difficult to remember. And of course, it's going to give you a tough time. So try and understand that it's easier, simpler, everyday stuff for which we need a standard unit. So I won't be wrong if I call it a standard unit. I won't be wrong either if I call it a chemist secret unit. Because you won't see mole written in any of the market stuff. Market has nothing to do with moles. They go with masses, counting, volume, concentration. Mole is actually for the chemistry people, right? I hope now it makes a little more sense than it previously did.
Yes,
Does it?
sir.
Okay, good, good. So let me export an image. Great. So uh, if this makes sense, let's move on and consider the first formula for mole. And what we're going to do is that we are going to consider this one. See, I wanted to do this one. Okay, this one, mass and mole relationship. We can convert the masses of solids, liquids, or even gases. This was just for explanatory purposes. We are even going to take solids, liquids, and gases for mass purposes. And I'm going to tell you how to convert mass into mole and moles back into mass. Okay, so
Yes,
I'm going. So let's start with the mass mole relationship. First, I'm going to write the formula, explain the formula to you. How is that formula usually twisted and manipulated for questions? Then we are going to solve some questions to really understand those manipulations. So let's get started. So moles, or we can simply write number of moles, the formula for which is MOL, mole itself, is equal to mass. And I really tend to keep these formulas as short as possible. That's why I'm not writing the whole stuff, mass of substance, mass of this, mass of that. Yeah, we understand whatever stuff we're talking about is going to be the substance. We're going to take its mass, and then we're going to move forward. Okay, so I don't know why I can't see this. Okay, good. So we call it molar mass, or molar mass is just another word for MR of the substance. Okay, now let me tell you that MR is gram per mole. Now, you're familiar with something that MR is always calculated from the periodic table. If you have the name or you have the formula, you can easily calculate it from the periodic table. So as soon as the question starts and you have the name or the formula, this denominator is not going to be a problem for you. So what's going to happen is that either one of these quantities, this or this, one of this would be given in the question, and one of this is you're going to find out. So either you need to find out number of moles and the mass is given. In that case, you're going to divide it by molar mass. If the mass is something you need to find out, a number of moles are given, of course, you might need to take this over here, multiply it. You're going to either divide your mass by MR and find number of moles, or you can multiply your MR by number of moles and find your mass. So it just works these two ways. Okay, so let's clear this one up. Let's write a couple of questions. So what I'm going to do is that I'm going to give you two kinds of questions. For number one, you need to convert mass to moles, right? And for second questions, you need to convert moles to mass. Now, in order to do this, we need a key. My key is going to be about the units that we commonly use. I hope you understand that 1 kg or 1 kilogram is equal to 1000 grams. I hope you understand that 1 metric ton or simply 1 ton is equal to 10 raised to power 3 kg or is equal to 10 raised to power 6 grams. Both means the same thing. Okay, 1 gram is equal to 1000 milligrams, or 1 gram is equal to 10 raised to power 6 micrograms. This is something you need to remember because the unit conversions are not given in exams. You need to remember them by heart. So let's write the question. Question number one, you need to convert mass into moles. If the mass is not given in the standard unit of grams, you need to first convert it into grams and then convert them into moles. That's why the key is given up top. Okay, so let's move on. So you have 1 gram of, sorry, it shouldn't be salt alone. I should be writing table salt, which the formula for which is NaCl. Okay, question number two. Let's say you have 100 grams of sugar that we eat every day, and the sugar that we eat every day has the formula of C12H22O11. Big formula, right? A little bit of calculation is definitely required for it. Question number three, let's move on. 2.34 metric tons of CaCO3 calcium carbonate, which is present in the form of chalk or marble or limestone. Yeah, these are different forms of calcium carbonate, or at least they contain a big percentage of calcium carbonate. Okay, so moving on. For question number two, we're going to convert moles to mass. So 2.79 mole of ice. And ice is of course water, so the formula is going to be H2O. And convert them into, using an arrow, and you need to convert them into grams. For
Sir,
part two, yes,
for question number one, we need to find the moles, the number of moles.
yes, you need to convert this mass into moles. So of course you need to find number of moles. I'm going to solve one of these. I'm going to solve part one for question one and part two for part one for question two, both of them for your ease. Let me write the questions completely. This would give you a very good idea how to do it. But if you already have a grasp of it, you can continue solving. That I appreciate. But if you were away,
Okay.
just let me write a couple of parts more and we'll get back to its solution. Okay, so this time let's go with something different. 3.78 into 10 raised to power minus 3 moles of glucose, and the formula for glucose is C6H12O6, and we need to convert them into kilograms. I'm writing the units so that you can convert them into the exact units they are supposed to. Okay, and the last part in this case, okay, 1 mole of MgSO4.7H2O. And you need to convert it into grams too. Okay, let's try and solve this. So we first need to calculate MR. MR is Na, and we need to find Cl. Na is 23, Cl is 35.5. I hope you understand that this comes out to be 58.5. So we need to find moles, and moles is mass, which is 1 gram over 58.5 gram per mole, right? You gotta cancel gram and gram. 1 divided by 58.5 should give you the answer in mole. Easy enough?
Yes, sir.
I hope it's not written too small. My habit of putting words inside into one another usually turns up in a very small font. I hope it still is readable, right?
Yes, sir.
Okay, if you're done with this, can I solve part one of the other question too? Your voice broke off. I wasn't able to understand what you just said.
Yes, sir, you can do it.
Okay. Would you like me to solve part one or any other parts? Because there are other parts with conversions. Would you like me to solve part two since you require conversion with it?
Oh, okay, sir.
Okay, let's try and solve part two. So I'm going to solve this one over here. First of all, we need to find MR. So for MR, we understand it's C6, we understand it's H12, we understand it's O6. So it's 6 multiplied by 12, which is the mass of carbon. It's 1 multiplied by 12, which is the mass of hydrogen. And it's actually 6 multiplied by 16, which is the mass for oxygen. And that's how the total comes out to be 180, I guess. Yeah, 180. Because 12 into 6 is equal to 72, 1 into 12 is equal to 12, 16 into 6 is equal to 96, the whole is equal to 180. That's 180 grams per mole. That's just MR. We need to still calculate the mass. In order to calculate mass, I hope you understand we need to rearrange the formula and we're going to multiply the moles with MR. So the moles are 3.78 into 10 raised to power minus 3, and sorry, I forgot to write the units. Getting back to it, mole multiplied by 180, and that's gram per mole. So of course, we're going to cut mole and mole out. We are left with the value in grams. So can you help me quickly with your calculator? Multiply 3.78 into 10 raised to power minus 3 into 180.
Yes, sir, the answer is 0.68.
So the answer is 0.68 what? That's it, 0.68?
It's 0.6804.
0.6804 grams. Now, when we convert it into kilograms, the answer should be divided by 1,000 and it becomes 6.8 into 10 raised to the power minus 4. 6.80 into 10 raised to the power minus 4 kilograms. There you go. Is it the same answer with your calculator too? 6.804 into 10 raised to the power minus 4.
Yes, sir, it's the same answer.
Great. Uh, After which I hope you understand what this is about, right?
Yes, sir.
Good. So